Last time we covered some stuff on the metric tensor and the contravariant and covariant objects in the context of general relativity. And so I'm just gonna provide a quick summary on this so far. So we went over what would happen if we had some space here, right? There's some three-dimensional space, and at every point we established the fact that there is this thing called the metric tensor, such that we have sort of this going on here. So I like to draw this picture where we have a lot of stuff going on at one point in space-time. So for a contravariant basis, and then we had a covariant basis. If we have some Cartesian coordinate system, I'm just going to do two-dimensional right now here, but in general, this could be n dimensions. And we have some distance, ds, and we have our unit vectors, our unit basis vectors that are orthogonal to each other. All right, so this would be dx2, and this would be our dx1 vector, our vectors. You could think of them as E1 or E2. And these are contravariant basis vectors. These are the basis vectors. So these things are vectors themselves. They're contravariant because they have upper indices here. Covariant basis vectors would have lower indices, like this. And we found that for an object like a force is a vector, and itself, the component, there's two sort of parts to a vector here. The component, right, the component and the basis along which you're measuring that component. And for force, we said that the magnitude of the force, and sorry about the dog in the background there, the magnitude of the force was contravariant. And so in order to get or not the magnitude, the component of the force along some direction is contravariant. So therefore, we have to say that its basis is covariant. And likewise, like something for like an electric field, we have the opposite right here. So this contravariant basis here, or this covariant basis, this is right here, covariant basis. This is a contravariant basis. So this would apply, the contravariant basis would apply to something like E mu, and the covariant basis would apply to something like F mu. Right? And from this, we established that there was a GMUNu that took us from these basis vectors to the real numbers. Right, and same thing here. We had a GMUNu, but upper indices, that took us again to the real numbers. Okay, and so, and then we realized here that GMUNu times GMUNu on the bottom is equal to unity. In other words, these are inverses of each other, right? So this is within 2 lectures here, I wanted to get really quick into this. I didn't really, easing into this kind of stuff makes it kind of boring, right? You quickly want to just move on to something else. So there's a method to my madness here, and the madness is jumping straight into the meat of GR, where we're looking at this GMUNu, and we want to look at its various forms. The most common form is the Schwarzschild form. That we're going to go over. There's a lot of analysis on this form where we'll be able to see what the dynamics looks like around a black hole, for example. This is the form that we're going to be interested in, and then we're going to go deeper, and we're going to look at other different types of forms that this GMUNu can take on. But nevertheless, this is sort of the summary so far of what we've gone over. Right? We went over the contravariant basis, we went over covariant basis, and we went over different types of vectors in the real world that we could be able to, or that we theoretically should be able to calculate and measure, and how these things are related to the real numbers. This thing will take us to the real numbers here, this GMUNu. It'll take us to because the real numbers are effectively what we end up measuring. We end up measuring values that are real, right? Not complex or imaginary or anything like that. All of these calculations are basically to say that all these calculations involving GMUNu, involving this object, are basically means to an end. And the end is calculating these special numbers that correspond to the curvature of space at some point, the distance, how we measure distance at some point if that space is curved, right? And so there's a lot going on at one point in space-time. Remember, this is a point in space-time, so this P here, this P has coordinates. It has T, X, Y, and Z coordinates. It's not just space, but it's space-time, right? So we could take any vector here. We could take any vector in this point. This point contains tons and tons of vectors in here. They're all 4 vectors. This defines the basis of a 4 vector. This is the basis of a 4 vector, right? Such that when we can apply something like this, a 4 vector, we could just call it F, or E mu nu is some 4 vector. It doesn't necessarily, in this case, it doesn't necessarily have to be the electromagnetic field. It could be anything. It's just some 4 vector. And when we apply GMUNu to it, we get a transformed, not a transformed, but a new vector, a new 4 vector, a mu vector, right? And we'll see why all of this is possible, why this is equal to this later on. But I wanted to just dive straight into the meat here. I want to be able to say, okay, we've effectively established the existence of this guy and the existence of this guy. Okay? We could theoretically, therefore, take any 4 vector in this point in space-time and do things to that 4 vector with these objects, with this object right here. And so, with that being said, I'm going to go into an example calculation now. Right, and so what are these 4 vectors? We can describe any sort of dynamics in terms of any sort of 4 vectors here, but what I found to be sort of illuminating, if you will, while studying this kind of stuff, was the fact that there are some very special 4 vectors that can help us describe the dynamics of systems throughout the universe. And some of these will include, so if I were to make this picture a little bit more complete, would be, again, this is still sort of an overview of what's to come, but still we have these special 4 vectors. We have the electromagnetic 4 vector. So electromagnetic 4 vector. V looks like an R. And then we also have our current density 4 vector. Current density 4 vector. And there's also the energy momentum 4 vector. And these things are interesting. These things will tell us a lot about what is going on out here at this point, right? And so the electromagnetic 4 vector is usually denoted with an A, like this, A mu, at the location P, and it has some basis, dx mu. The current density 4 vector is usually denoted with a J, J mu. Again, these are vectors. Again, it's located at point P, and we have some D, and we have a basis, and we also have the energy momentum, and I think that's usually denoted with a P. This is a little bit redundant. So this is the 4 vector, this P mu here, this dx, and this P right here is at the point P. So the point P sort of denotes the name at the point, whereas this P right here sort of denotes the name of the vector at that point. So this is like the vector at point P, vectors at point P, right? And so we could theoretically take 2 of these vectors, right? We could take A mu and J mu, and we can figure some interesting things out given this metric here. And I will just write these out in their entirety, where this is this should be over some scalar. C is the speed of light. This is some scalar value that sort of permeates, that exists throughout all of space and time. And then we have our spatial components, AX, well actually, if I'm going to do this correctly, this should be in the X direction, the component of A in the Y direction, the component of A in the Z direction. So this is a 4 vector because this is sort of the component of this right here, sort of the component of A in the time direction, right? And same thing here, where we have C times rho, which is the density, and then we have J in the X, current in the Y direction, and the current in the Z direction. And same thing right here, where we have 1 over C again, the energy at some point in time, and the momentum, P in the X direction, P in the Y direction, and P in the Z direction. Again, this is sort of P in the time direction, and this is right here, this is J in the time direction. So we have these 4 vectors. So if I were to sum this up even more, sort of collapse this space-time diagram even more, where we have some space, some 3-dimensional space, and at some point there's a couple of objects we want to take note of. We want to take note of GMUNu, A mu, J mu, and P mu. These are all 4 vectors that exist at some point. We also have G mu nu. All right, so we have tensors that exist at some point, and we have 4 vectors that exist at some point. And this is all dictated by point P, right? And we're going to eventually be interested in how many of these vectors actually change, how many of these vectors change as we traverse space and time. So as we go, say, from point P to point Q here, as we make this change, how are these guys going to change? How are these objects going to change? And we're going to find some interesting properties there. And with that being said, this isn't the whole story, however. Again, I want to dedicate these 2, maybe even 3 videos to a summary on GR before I actually get into the sort of the nitty-gritty here. We have, again, like I said, we had this Schwarzschild SCH, I think, CS Schwarzschild metric is going to be our most interesting metric, but then we have other types of metrics. So we have the Kerr metric, and these are all variations on this guy right here. We have our Ernst, E-R-N-S-T metric. We have other different types of metrics that satisfy. These all have to satisfy the Einstein field equation. The Einstein field equation. And so these are we can't arbitrarily pick. We can't arbitrarily pick these guys. These guys have to satisfy. If we want some interesting physics, and we want to see what the physics looks like, there's a finite set of these metrics that satisfy this Einstein field equation. But aside from that, we are interested in that's just half the story when it comes to GR. We are also interested in Lagrangians and the dynamics of systems and the dynamics of an expanding universe. And with that being said, we want to take a look at stuff like this. I will explain what all these terms mean later. I just really want to introduce ourselves to these topics before I go deep into them. And some of you who know GR and who know this physics well know what I'm writing out. This is the sort of a modified version of the Friedman-Walker-Robertson formula. Right? And so the constants, these types of constants are going to show up in the Einstein field equations along with this other interesting constant, the gravitational constant, this thing that Einstein came up with when developing his equations. And ultimately, many of these constants that we're going to find in deriving these formulas, many of these constants, this one here and this one here, are going to show up in many metrics, in many of these different types of metrics, right? And if I remember correctly, the Ernst metric contains this in here, this guy right here, inside GMUNu. So inside GMUNu, these guys will show up, right? So we have to talk about the dynamics of expanding universes as well. And we have to talk about how many of these constants get embedded into the Einstein field equations. And we're going to go deep into that. We're going to take a look at how these guys are ultimately tied in with one another when it comes to assessing the dynamics of an expanding universe and the dynamics of sections of universe within the proximity of black holes. So I put this back on a new screen here because, shift this over a little bit, because I actually want to derive this, and in the next videos to come we're going to get deeper into GR and some of the mathematics behind GR, but this equation will sort of rear its head later after we've established some other concepts. And so this formula, this Friedman-Robertson-Walker formula, basically comes from modeling the universe as if it was kind of like a rubber band. So if we have a rubber band, let's see, why isn't my pen working? There we go. So we have some rubber band cut at both ends, and we mark the rubber band at different locations equally spaced apart, like this perhaps. This distance here is delta x, and we stretch the rubber band by some stretching factor a, right? And as time, so we can, if we stretch it really tightly, or if we stretch it really fast, really quick, a might be large. If it's not so quick, a might be small, but a is a function of time, so we can stretch this rubber band as much as we want. So the distance between, say, point A here, say we'll call this point A and we'll call this point B, or marker A and marker B, the distance between the two is delta x at some time times a of t. So a of t is going to be some number. So the distance here is delta x, but when we stretch it, it's gonna stretch out by some factor, a as a function of time, right? So if we were to simply take the derivative with respect to time of this changing distance, we get that this is equal to, put some notation here, d dot, this d dot is the same thing as the time derivative of d, is equal to the change in x times the a dot of t. Right, so again, the delta x here is a constant, so the only thing that has a time component to it is this a of t. Right? So the time derivative of a distance, again, is the velocity. So we have this right here. Okay, now I'm going to do something a little bit weird. I'm going to say that v is equal to d change of x times the change of a with respect to time times a with respect to t over a with respect to t. All right, so I have done nothing here. I'm just multiplying by 1 because the same one thing over this is the same as this is 1 right here. Right, so but what we see here now is that this guy here and this guy here, well, that's just this right here. Right, so we can actually change this a little bit, and we could say that v, we could say that v is equal to d times a dot, the time derivative of a, over the non-time derivative of a, like that. And we're going to call this right here is h. So essentially what we have is that v is equal to d times h, where h is Hubble's constant. H is Hubble's constant. Okay, so this is going to show up later. So this is sort of the elasticity equation for the expansion of the universe in terms of distance and Hubble's constant, and how the velocity of this elastic model changes, or what the velocity of this elastic model is. So let's invoke some physics now. If we invoke some physics, we say that F is equal to GMM over R squared. And in this case, R is the distance, so we'll actually just replace R squared with D squared. It's the distance between two objects in the universe, so we'll call it D squared. And the potential energy, actually, to be a little bit more conventional, potential energy is usually U, right? And that's equal to the negative of the derivative of the force, which is just this, but over D instead of D squared. All right, so that's a G. And so now the total energy here is, so I'll say total energy is equal to the kinetic energy plus the potential energy. We know that the kinetic energy is 1/2 mv squared minus g big M little m over d. All right, so this is the total energy of our system, of our elastic system. And so what I can do now is say that this is equal to k. This is equal to some constant. Right, so this constant actually is going to show up right here. That's this constant right here. Okay. And so we can, if we were to, we could divide both sides by k and multiply both sides by 2, right? And what we end up getting is that v squared, or divide both sides by m, sorry, I think that's what I meant. You divide both sides by m and multiply both sides by 2. We get v squared minus g m 2gm over d, see if I'm getting this right, is equal to k. All right, so k, this is a constant, so when I multiply it by 2, it just becomes another constant, and when I divide it by little m, it just becomes another constant. Right? And again, the little m is the mass of some body, and the big M is the mass of another body. Right? We're just dividing by a constant, essentially, when we do that. So now we are left with this equation. So what we can do now is invoke some of our elasticity conclusions here, over here. So what we have is d, so this d right here, I'll just rewrite it. D is equal to the change in x times a of t, and v is equal to the change in x times a dot of t. That's something we said right up here. Okay, so we'll actually just plug this in. We'll plug v into here, so we get change in x squared times the a of t squared minus 2gm over delta x a of t equals k. Right, so we plugged everything in, and so we have this equation now. Right, so now we want to consider a little bit more. I wouldn't say I call this physics per se, but I will rewrite. Actually, I won't rewrite this. I'm going to bring it way up here. Give myself some more space. Give myself some more space here. If we consider that the mass of the universe is equal to the volume of the universe, the volume times the density, then for the volume of the universe, if we were to treat it as some sphere, if we were to think of the universe as some sphere, the volume is 4/3 pi d cubed, and the density we'll call rho of t. Right, so we don't really know exactly what the density is, but nevertheless, we can still write this. So the mass is equal to that. So we can actually plug that in. This is big M, right? This is big M, the mass that shows up right here. So we can actually plug this in. If we plug this into the equation here, we get this a of t squared minus 2g times 4/3 pi d cubed rho of t. This all here is m, divided by delta x, and all this down here, so a of t equals k. All right, well, we know that this guy here, this is the distance d, which is what we had right here, if this is just cubed. So this is cubed a of t cubed. So we can be able to do some canceling. All right, so if we do some canceling here, some of that's going to cancel with that, some of that there's going to cancel with that, and what we end up getting is the following equation, which is this times a of t squared minus 2g times 4/3 pi delta x squared a squared of t rho of t equals k. We're almost there. This is sort of a quick and dirty derivation of this. Okay, so now what we can realize is that there's a delta x squared, which is a constant. So delta x squared is a constant. So we could divide all sides by delta x squared, and we just put that back, we just absorb that into this constant. And with that in mind now, or with doing that, we get a, this should actually be a dot if I think I missed a dot in here. That should be a dot. I think I lost that dot down here. Okay. So we get a dot squared minus, we'll actually condense this a little bit. 2 times 8 divided by 3 is 8 pi g over 3 times a of t squared times rho of t equals k. Okay. So now, if I divide both sides again by this guy right here, I get a dot of t squared over a of t squared. I'm sort of putting the square inside and outside. I'm bouncing between those two. It's really no different. It's just these functions squared minus 8 pi g over 3 times rho of t equals k over a of t squared. So this is pretty much the equation now. This is pretty much the equation because we said this is it right here. I just moved some things to the other side of the equation where I said I just basically moved this guy on one side. Right? And the k here can be a negative constant or a positive constant. Right? And so we end up with that equation. We have a of t squared a of t equals 8 pi g over 3 times rho of t minus k a over t squared, where k in this case is a negative constant, right? It could be plus, it could be minus, but nevertheless, this thing here is what is the Friedman-Robertson-Walker formula that we simply derived by invoking some physics. Here's the physics that we invoked. We assumed again that the universe was a sphere, right? And we used an elasticity model right here. So we did some elasticity, and we invoked some physics and some basic concepts in volume and density, and we arrived at this formula. And if we take this one step further, this is Hubble's constant, right? This right here is equal to all of this, right? So Hubble's constant is a function, or as a constant, is based off of the density of the universe, and this k showed up here sort of like a Hamiltonian almost, this k here. So if we wanted to, we could say this is the almost like a Hamiltonian constant divided by a squared, right? This is the formula. This is the formula. And with that, I will move on to the next video where we'll get more into the math of GR. So I'll see you in the next one.